Hi everybody, we're going to start as usual in this class for week 12 with a recap of what we covered in the last set of classes, which was actually back in week 10. And so I'll provide a summary of what we learned, and then we'll go on to think about what we'll study in today's classes. Thank you, and thanks for listening. Hi everybody, so let's talk about this summary of the week 10 class 2 work. So in that particular case we considered the hydrogen atom, and of course now we don't just have the kinetic energy of the electron as it whizzes around the outside of the atom. We also have the potential energy, and it's this potential energy that keeps that electron in place. It's that attraction between the proton and the electron that we start to build into the Hamiltonian operator now. So the Hamiltonian operator H hat. And so if we think back to our quantum mechanical rules, the first approach is to consider the system in classical terms. So we now, of course, have this kinetic energy and we have this potential energy. Then we start to build the operator using substitutions for the momentum typically. And when we think about the momentum, when we're considering this spherical situation where we have this atom and it's spherically symmetric, this is where we have to start to recognize that del squared has to be used in terms of spherical coordinates. So we looked at that in the previous classes. We then built the Schrodinger equation around our Hamiltonian operator that included del squared for those spherical coordinates. We built that Schrodinger equation, and then we compared it back to the work that we'd done in chapter 6 regarding the rigid rotator. The new parts to the Schrodinger equation included these radial terms. So there were 3 terms in the Schrodinger equation. So the new ones to us were terms 1 and 3. And the second term we've recognized before was that L hat squared term. It was the same as for the rigid rotator. So if we now continue to move through the summary, what we now know that we can do is we can separate the Schrodinger equation using our familiar separation of variables approach that came up in chapter 2 of the textbook. So that's in here. We also have a solution, therefore, to the radial equation. And so we spent some time looking at that solution to the radial equation, and we found these radial wave functions. Again, we didn't actually go through the full solution and the solving of that differential equation, but we found that these radial wave functions did depend on 2 quantum numbers n and l, and the solutions were in terms of these associated Laguerre polynomials. And what are these associated Laguerre polynomials? Well, they're fairly complicated to set up. So again, we'll just jump to the conclusion here. But what we must recognize is that each radial wave function, and this is going to be familiar moving forward, so the simplification here is that each radial wave function, so this is the radial wave function, is a polynomial multiplied by an exponential. So there's always going to be this exponential decay as we move out towards r equals infinity. We also considered the volume element that is associated with the volume of a shell. Right, so we're considering now just the r term. So if we integrate over psi theta d theta and d phi, we find that those terms become 4 pi. And so once normalized, of course, they turn out to be 1. But what we're caring about in this particular case is the r part. So it's this r part of the spherical coordinates volume element, right? So the volume element in spherical coordinates, so that's like our d tau term, but in spherical coordinates is r squared sine theta dr d theta d phi. So when we just consider the r parts, that's this r squared term and the dr term in here, and it's those pieces that find their way into the integral that I've just described. Of course, the wave function itself, we must recognize that we've got this incrementally new wave function, the radial piece, and then we still have this angular piece that will become very familiar to you because we covered it for the rigid rotator. If we go to our textbook, Macquarie, we find that table 7.3, that's on page 325, that provides us the first few hydrogen atom wave functions. So that incorporates the whole thing in here, and we'll see them in that table 7.3. Okay, moving on to a second page of the summary. So again, I've repeated the normalization condition, and this is an integral again with respect to d theta, d phi, and dr. And now I've got the Kronecker delta on the right hand side in here, which also takes into account the orthogonality. We can also rewrite this in the bracket notation. And lastly, this is more a summary of the implied learning from the last set of classes. What we find is that the wave functions that we've developed, because those wave functions are also eigenfunctions for L hat squared and for LZ hat. So these wave functions are all eigenfunctions of all three of these operators. It turns out that these operators mutually commute, and so how would we describe that mathematically? We're going to say that h hat, the Hamiltonian operator, does commute with the magnitude of the angular momentum, that operator squared, so that's equal to 0. We also recognize that the Hamiltonian operator also commutes with the angular momentum in the z direction, and therefore if these two commute, then we also know that, and we've demonstrated this in chapter 6, we also recognize that the angular momentum magnitude operator squared and the angular momentum in the z direction, that operator, they also commute. And so again, this is just restating this particular case. So this assures us that these eigenfunctions simultaneously are wave functions or are eigenfunctions for all of these three operators. As a result, the wave function that comes out of the solution to the Schrodinger equation, so the wave function that comes out as a solution to the Schrodinger equation, depends on these three quantum numbers. These come out of the mathematics, n, l, and m sub l. The energy operator, so the energy only depends on n. So n is the quantum number associated with the Hamiltonian operator. It's the energy quantum number. We also have the angular momentum L that's associated with the angular momentum, the magnitude of the angular momentum operator squared. So we call this the orbital angular momentum, and therefore L is the angular momentum quantum number. And lastly, in here we have a quantum number m sub l. That's the quantum number that's associated with the LZ operator. So this is the z component of the orbital angular momentum, the z component of the orbital angular momentum. So this is all a summary of what we've covered already in classes that are going to continue now in week 12. We're going to ask ourselves the questions about what are the shapes of the orbitals. We're going to recognize that there are three coordinates. We have an r coordinate, a phi coordinate, and a theta coordinate. And so because we have these three coordinates, it's going to be difficult to try to visualize the shapes of these functions, and indeed the shapes of these orbitals. So that's going to be our quest today, to answer the question, what shapes are the orbitals. We've already considered in week 11 the radial distribution shapes for the H atom, at least in the 1s, 2s and 2p orbital, and also in the Pogel exercises for chemical activity 8 that you've covered. So let's dive in on the next video.